Okay, guys. So, uh, can you give me the example of the last class because you know that I'm teaching from my mind about Jacobian? I mean that what was the state equations? dm1. I remember that was second order system. dm1 is equal to m2, and dm2 we came up with what? Can you please read that if you have it from your notes? If you have, I mean, nonlinear version of that. Do you have it, guys? Yes. Negative 4m what? m1. That's right. And uh-huh. 4m what? I'm not sure, but so are you sure? Okay. Any guy do the other guys that you have any notes in front of yourself? Okay, so doesn't matter. So I'm gonna teach you the concept of Jacobian. I'm gonna teach and the other example. So suppose that you have the x double dot plus this system plus plus 4 2 x dot plus 4x um, x dot plus 4x equals to 8, right? Equals to 8. So having that, now you know that we can go to state space. Now you're expert of that. M1 is x and the M2 is x dot. So you got from here dm1 as we write in MATLAB, right, is m2 and dm2 is x double dot, which from here x double dot equals to minus 2 m1 in m2 minus 4 m1 plus 8. So we got nonlinear ODE in the state space representation. dm2 was minus 2m1 m2 minus 4 m1 plus 8. So I told in previous class the first step is to find the equilibrium point of the system. And I told you when I said the equilibrium point of the system means the velocity and acceleration is 0. So this is velocity and this is acceleration. See? Because dm2 is velocity. Here we go. dm1 is velocity. See? m2. And dm2 is acceleration. Here we go. So when it's at 0 means m2 is 0. Means velocity is 0, obviously, because it's the equilibrium point of the system. And this when the acceleration is 0, because this is 0, from here you get that m1 is 2. Here we go. This is, and we are showing with the star, means the equilibrium points of the system. So equilibrium point of the system, so m star 1 is 2, and m star 2 is 0. Velocity, and if this x is position, it's going to be position. It can be an if, as Oscar said, he's gonna continue for thermofluid. Maybe it's gonna be temperature and the rate of temperature. See what I'm saying, guys? Okay. So after finding that, I told you that you have to find Jacobian matrix. Jacobian matrix. I told you that we name this the right-hand side as F1 and here as F2. Remember from the previous class? So what you're gonna do, you're gonna have this, as I told you, round F1 over round M1, round F1 over round F2 means partial derivative, round F2 over round M2 of F1, round F2 over round M2. At where? At the equilibrium points M1 and M2. Being said, so F1 over M1, we don't have any M1 here, so it's gonna be 0. M2, 1, because you have only M2. F1, M2, so minus 2 M1 minus 4. See, the derivative with respect to the M1. With respect to M2, sorry guys, I made a mistake here. With respect to M1, minus 2 M2 and minus 4. Now with respect to the M2, only term is here. Minus 2 M1. At where? At the equivalent point of 2 and 0. Clear, everybody? Yes? Yes, guys? So, yeah. So, partial derivative of the f1, we named the right-hand side of this as f1 totally, here, okay? And remember the previous class, and we're gonna name this as f2, okay? Partial derivative of f1 with respect to parameter m1. So, do you see any m1 here? Okay, so its partial derivative is 0 because there is no m1 here. So f1 with respect to m2. Do you see m2 here? Yes. So like as remember I said y is equal to x. Dy over dx is how much? 1. So df1 over m2 is how much? 1. Clear? Yes? Now f1 with respect to m2. Oh, good. F2. Why I said 1. Okay. F2 with respect. Yeah. Okay. F2 with respect to m1. Oh, everything is 8 morning. Okay, that's why you're confused. F1, F2 with respect to M1. Yeah, that's right. I only have to change it. Okay, so F2 with respect to M1. That's right. So F2, what is M1 terms here? This term and this term. So with respect to M1 gonna be minus 2 M2. That's right. Right. And minus 4. Now F2 with respect to M2. Only M2 is here again. Minus 2 M1. See what I'm saying? So, yeah, this is right. Only I had a typo here. So J, Jacobian matrix, I'm writing here 0, 1, minus 2, M2 minus 4, and minus 2, M1 at the equilibrium point. Equilibrium point, I'm showing the star. So if you do that, Jacobian matrix is going to be 0, 1. M2 star is 0. So the remaining going to be minus 4. So M1 star is 2. Going to be, again, minus 4. I just replace here 0, 2. Understand? So this is nonlinear differential equation, x dot, nonlinear state space representation. So now you can say simply after transferring, you can say after linearization, you can say dm1 is m2 again, and dm2. Okay, now look at here, guys. On the other hand, guys, we can write in the matrix form dm1 is dm2. Get here, right hand, left hand side. Now this, we can say it is Jacobian in m1 and m2. So Jacobian obviously is 0, 1, minus 4, minus 4 in m1, in m2. This is matrix operation, that's right. 0, m2, bingo. Minus 4, m1, minus 4, m2. Minus 4, m1, minus 4, m2. So now this is linear terms, not nonlinear, that multiply together. Okay? See what I'm saying, guys? So you change nonlinear state space representation to linear state representation by Jacobian. This is another way of the Taylor series expansion that I taught you in the beginning of the semester. So the question is that what's another property of the Jacobian matrix? I taught you Roth stability criteria to judge the stability of a given system, right? When you go to grad school, few eventually, the fundamental of that you can judge the stability of the system by Jacobian. How? You have to have the eigenvalues of, do you know what's eigenvalues? Lambda I minus j is 0, determinant. Have you heard of eigenvalues? Yes? Everyone? Okay, so for a given matrix, eigenvalue, okay, lambda I is the unit matrix minus j. So let's do that together. So because Jacobian is 2 by 2, eigenvalues must be, the unit matrix is 2 by 2. So you're going to have lambda 0, 0, lambda. This is unit matrix minus j 0, 1, minus 4, minus 4. Determinant is 0. So it's going to be lambda minus 1, 4, lambda, because this is plus minus 4. Minus and minus and plus. Yes. So you know determinant of a 2 by 2 matrix, if you remember from high school or university, A, B, C, D, its determinant is AD minus BC, diagonal. So it's gonna be, oh, not 0, it's gonna be lambda in lambda minus 4 minus 4 in minus 1. This. So this is gonna be lambda square minus 4 lambda plus 4 is 0. So this gives you lambda minus 2 square is 0. So you have two eigenvalues. Plus 2. Okay? You have two eigenvalues. But the question is, let me double check everything, guys. Okay. This is plus. That's why you say something is wrong. Okay. So you have two eigenvalues. Minus 2. Okay? So if the all please write it down. All eigen values of a linearized state space equations are negative, the system is stable. Here we go. So your system is stable because both are minus 2. Or if I want to write it more accurately, if all real parts of eigenvalues of this is real number, so we don't care here. Understand, everybody? So going to the MATLAB, because I told you I want to make you expert of MATLAB as good as I can. So if you go to the MATLAB, and I have to teach you how to calculate eigenvalue, okay, in MATLAB. Even symbolically, okay. Even symbolically, okay. First of all, our let me open a new. Suppose our Jacobian that you calculated by the hand was 0, 1, 0, 1, minus 4, and minus 4. First of all, I'm going to say A is eigenvalue. This gonna calculate eigenvalue of a matrix given. This is command in MATLAB. Let me save it as in 430. Example. Okay. So if I run this, it says minus 2 as we got. See what I'm saying? Everybody? Yes? So eigenvalues is like that. Or if I say another matrix, say Jack 1, Now I'm giving you third by third matrix. It means that you have third state variables. One, say 0, 0, 1, I don't know, 0, 3, 4, minus 2, 3, 5, 9. I don't know what the system is. If I say I jack 1, okay. Now if I run this, okay, let me close this. And always I'm going to say CLC clear all. This I'm going to share with you. Okay. Okay, this system has a complex numbers as eigenvalues. Do you see this? Yes, everybody? Huh? So, but its real part is positive or negative? Its real part. Tell me. Huh? Positive. Means that your system, whatever it is, I don't care, is unstable. If this is a linearized version of that, Western Jacobian. You get my point? Everybody? Yes? Huh? Okay. So, and now there is a command Jacobian. Okay. Jacobian matrix. If you go to the help of MATLAB, because I'm going to teach you eventually. Okay, guys, look at here. It says you have this. These are the vectors of that. Okay. This is your F1, F2, F3. And you have three state variables. You say sims this, Jacobian gonna give you that. Let us do that together for the example that I have done. Okay. Jacobian has symbolic things in MATLAB. Okay. Look at here, guys. I'm just copying, putting here. I'm gonna say M1 as we did. That's right. And M2 for our system. Our parameters to make a Jacobian is M1 and M2 for the second order system. See exactly what I'm doing here. See here, M1. So your F1 is M2. I'm just typing here. So it is M2 and your F2. Oh, where are you? Minus 2 M1 M2 minus 4 M1 plus 8. So minus the second row is minus 4 multiplied by M1 in M2 minus 4 M1, right, guys? Plus 8. Here we go. Two-state variable F1, F2. I just typed here. Minus 2 M1. M2 minus 4 M1 plus 8. Now if I run this, okay, you're gonna get this, guys. You're gonna get exactly this matrix. Look at here. Exactly what you have to get this. So let me run it. What? Oh, it says that this is not allowed. Okay. So let me say X and Y. Doesn't matter. M2 gonna be Y. It's gonna be X. This is gonna be Y. This is gonna be X again. X. Y. Y minus 4x and minus X. Okay. Okay, here we go. Look at here. 0, 1, as we did. 0, 1, minus 2y minus 4 minus what? Oh, I said here is minus 2. Sorry, guys, I have to read it. Okay, minus 2y minus 4 minus 2y also minus 2x. Do you see that? Yes, everybody? Huh? You got it? Yes? Now I want to find the value of the eigenvalue. I'm gonna say matrix B. Okay, look at here, and let me remove this from here. So I say your matrix B is this. What I'm gonna do, I'm gonna say now put some values. I'm gonna say your equilibrium point x is equal to how much was 2. Equilibrium point of y was 0. So at M1, I'm just commenting here to make you understand because this is your M1 and this is your M2 equilibrium point. Equilibrium point. So what I'm gonna do, I'm gonna say value of Jacobian is eval. This is command in MATLAB in B. Eval of Jacobian by putting these numbers inside here, inside the answer. So if I do that, hopefully it works. Yeah, it's 0, 4, minus 4, minus 4. Do you see, guys? 0, 4, minus 4, minus 4. See? Everybody? Understand? Then, now I'm just deleting from here. Now you know how to code it symbolically. Then I'm going to move it put here, guys. I'm going to say eigenvalue of Vj. Calculate for me. Here we go. I'm commenting everything now. I started from nonlinear states representation, then gave by Jacobian, then gave the equilibrium point, then I evaluated the Jacobian at the equilibrium point, and then I said calculate eigenvalues for it. See, here we go. Minus 2, minus 2. Everybody clear what I have done? Yes? Yes, guys? Good. So let me go to another example that is third order system. Okay. Go back to the notes. Okay. So let me say so let us say x triple dot plus 4 x dot square in x plus 5 x dot plus 10 x equals to 20. So you know that because third order system, how we do it in the state space representation? What? No, we are in Jacobian, man. I'll give you 5 minutes to transfer this to the state representation. Okay, we are done with the raw stability. You are in the Jacobian. I want to calculate the eigenvalue of the Jacobian to judge the stability. Okay, how we transfer it to the state space? And let me put this as x square, x double dot. Oh, what happened? Why it's not working? Okay, x double dot x. X double dot is stored in X. 5 minutes. Transfer it to state space representation in nonlinear form. Okay, guys, what's that? It's simple. What you're gonna do says M1 is X, M2 is X dot, and the M3 is X double dot. So if you have the time derivative, dm1 is X dot, which is M2, dm2 is X double dot, which is M3, and dm3 gonna be X triple dot. From here gonna be minus 4. X double dot is square. M3 square in X in M1 minus 5 X dot. X dot is M2 minus 10 in X 10 M1 plus 20. Clear, everybody? Yes? Huh? So again, this is your F1, this is your F2 for Jacobian, for F3. First, you have to find the equilibrium point, means the derivative goes to 0. From here, you get the equilibrium point of M2 is 0. Equilibrium point of M3 is 0. So this is 0. This is 0. From here, you get the equilibrium point of M1 is 2. Here we go. Now I'm going to use again Jacobian metrics in MATLAB, not by hand. Okay? So, here we go. I'm going to copy and paste everything here. For third order system. So I'm going to say, I don't know, x1, x2, and x3, huh? Because of m1, m2, and m3. Even you can put m. Let me try this time, like this, m3. So f1 is, look at here, m2. So you're gonna type here m2. f2 is m3. And f3 is minus 4 m3 square m1 minus 4 m3 square in m1 minus 5 M2 minus 5 M2 and minus 10 M1 minus 10 M1 plus 20. Okay guys, I just typed here minus 1 M3 squared 1 minus 5 M2 minus 10 M1 plus 20. Now I'm gonna say M1, our variables are 3. M2 got third order system. See, M2, M3. Now I'm gonna say M1 equilibrium point was 2. M2 equilibrium point was 0. And M3 equilibrium point was 0. This is again M3 equilibrium point. There we go. And I'm gonna name this as B1. Do not confuse with the above. And now we J1 gonna be equilibrium B1. Okay. And A1, I'm gonna say eigenvalues of this first order system. Here we go. Everybody understand? Yes? Yes, everybody? I just typed here. So let me double check everything to make sure that I typed 5x L1 minus 5 and 2 minus 10 plus L1 minus 5 and 2 minus 10 L1 plus 20. Yeah. So you get the equilibrium points, and that you put some space when you look at the notes, you understand what's happening. Okay. Now if we run this, equilibrium eigenvalue of this system is very interesting. One of them is real part is negative. The other two are a pair of complex conjugate values, but real part is positive. See what I'm saying? It means that your system is unstable. Linearized system is unstable. See what I'm saying? Yes. Everybody. So it says you have third order system, you're gonna have 3 eigenvalues. So 2 of the real parts positive, so it's gonna be unstable system. So its proof is very easy, guys. Look at here, guys, all of you. What was equilibrium point of what is that? Okay. M3. M3 is x double dot. Equilibrium point of that is how much? You tell me. How much? How much is that, guys? Equilibrium point of M3 is how much? Yeah. So M3 is x double dot. In linearization, I say, okay, bye-bye. So what's remaining this here is x triple dot. Look at me very carefully. Plus x dot plus 10x is 20. Guys, if I apply Laplace to this, it's gonna be s cubed because triple plus 5s plus 10 equals to 20. From here, I linearized, that's right, I eliminated linearized. You get, obviously you have x here. You get x equals to 20 divided by s cubed plus 5s plus 10. Guys, based on the Roche stability criteria, this system is stable or unstable. And if not, why? By just looking at it. Just look at the game. Go to your root stability criteria. See what's the first condition. Please go. First condition, not second. What's first condition? The first condition is all the coefficients must exist and be positive. That's right. Yes. So do you see the all coefficients exist? What we are missing here? What we are missing here? Yes, lady. We are missing S square. Now, even if that I use the things that now you're expert of that in MATLAB, saying your num is 0, 0, 0, 20, and then is 1, 0, 1, 0, 5, and 10. This is num, the denominator, third order system. If I say step num and then step function, it must show on a stable system. Obviously, it's 10 to the power of 27 on a stable system. So Jacobian proved you by showing the real part of the eigenvalue is positive, showed you that your system is unstable. If the real part of eigenvalues of linearized system is positive, even one of them, your system is unstable by Jacobian. Clear, everybody? Yes? Good. Now you tell me, because I'm going to wrap up the class. When I say, listen to my word by word that I'm asking, and think about that deeply and give me the answer. I say eigenvalues are positive. Your system is unstable. Does this remind you positiveness of a thing that you have already seen in my class? I'm just giving you hints. What is this, guys? What is this? When your system is unstable in the complex plane, I taught you. Yes. So poles are positive here. That's right. Yes, in this area. So eigenvalues is kind of what? What of the system? Kind of poles of the system. See what I'm saying now? Yes? Okay, good. When you graduate to go for working in this industry or go to grad school, at least you know that eigenvalues of dynamical system, its function is as the poles of the system. Now, bear with me. Sims X, what was your closure transfer function that we want to find the poles of this system? Okay, so poles of this system, I'm going to say poles is solve x cubed plus cs cubed plus 5x plus 20. Oh, plus 10, sorry guys. Plus 10. Right. Oh, guys, look at this. Okay, these are the poles of the system. Do you look at this? Yes? Everybody? Look at the numbers. Now look at the Jacobian of the system. What do you see? This is Jacobian. This is poles. What do you see? What do you see? Yeah. Jacobian of the linearized state space representation is the poles of the system. That's why if it's positive, look as the poles, your system is unstable. If they are negative old, your system gonna be stable. See what I'm saying? So now I'm just copying here because I'm gonna share with you, and this is the wrapping up point of the modeling of the system. So if I say, yeah, if I run this, you see that I'm gonna say name here eigenvalue to make, when you run this, you understand eigenvalue, and these are the poles. So if I run all of them together, oh, let me put down. You see that the eigenvalues of that in state space representation linearized is the poles of the system in the frequency domain, in the Laplace domain. That's interesting, right? See what I'm saying? Here we go. Poles, eigenvalues, exactly the same numbers. Exact. So poles of Laplace transform from characteristic equation, closed transfer function, are eigenvalues of linearized state space represented in time domain. So that's why we say if you want to have a stable system, you have to have all of them. Poles or eigenvalues, real part must be negative. If even one of them is positive, your system is unstable. Understand? And we are done. And pleasure meeting you guys. Let me first, hold on. Let me